Hi, and welcome to TEMEKO. In this lesson, we will talk about the global and body coordinate systems. You must be asking, how many reference systems do I have to use in this course? I promise that you will only have to learn about these two systems I've just mentioned. By the end of the video, you'll understand the benefits of using global and body coordinate systems in Multibody Dynamics. Let's start with an intuitive concept: velocity magnitude. Imagine this. You see a car racing in a Formula 1 circuit. One of the things you might be thinking is how fast the car goes. You might have an idea if somebody tells you that the car is going at 200 kilometers per hour. Why? Because you have been on a car going at maybe 100 or 120 kilometers per hour. Therefore, you can somehow relate these two speeds even though you might not have ever experienced 200 kilometers per hour yourself. Now, when you say that the car's speed is 200 kilometers per hour, there is always an implicit comparison. That comparison is with respect to what or who the car is going at that speed. You understand that there is a big difference in saying that the car travels at that speed while you sit on the sofa comfortably at home, or saying it while you are in the car. Now imagine that there are two people in the car going at 200 kilometers per hour. Incredibly, they have a ping pong table in the car, and of course, they don't miss the chance to start playing ping pong. If it's not crazy enough, imagine that you are given the task of calculating the velocity of the ping pong ball at all times, and report that to the audience watching the race. How would you approach this problem? First, you know that if you want people to relate to your findings, you need to report these magnitudes using a reference they can appreciate, as you did when I told you that the car was traveling at 200 kilometers per hour. Your first words are that you will be giving the information with respect to the place where you are standing. It means that where you are standing will become the origin of the reference system you are using to tell the parameters. Now, if the ball were in the pocket of one of the car's passengers, you know for sure that its velocity is the same as the car's. Now, the passengers started playing ping pong. The ball is no longer fixed with respect to the car, meaning in the pocket of the passenger. How do you tell the velocity? It is clear that it becomes way more complicated trying to define the velocity from your standing point, the origin. The ball not only has the velocity of the car, but it also has the velocity produced by the bounces and hits of the game. You try to estimate this velocity from your place, but there is no way it can be done. You think, what about if I ask one of the players to tell me what they see? You call the player on the radio and ask them to tell you the velocity of the ball. The player answers, sure, and continues, as I can clearly see how the ball is moving with respect to me, I can easily tell you the velocity of the ball. Now the player has become the point of reference in the car. The player has become a reference system traveling in the car. The player tells you the velocity according to the player's point of view, and then voila! You come up with the idea that if the player knows the velocity of the ball with respect to themselves, and you know the passenger's velocity from your standing point, then add these two, and finally you have some sort of velocity information. But sadly, it's not the way you wanted, because how do you transform the velocity given by the passenger to a velocity in your reference system? Good question. Let's check what we have until now. You, the estimator, understood that trying to figure out the velocity of the ball in the car was complex. You said that where you were standing was the origin of a reference system that everybody understands or can relate to. In this case, as you are standing on the ground, we will call this the global frame of reference or inertial frame of reference. Then you suspected that it would be easier to know the velocity of the ball if you asked that from the passenger. You have just created a reference system attached to the car. We will call this the body reference system. For you, it is simpler to say, what's the velocity of the car? And for the passenger, it's simpler to say, what's the velocity of the ball? Finally, you say that the velocity of the ball is the sum of both velocities. The one that you see plus the one that the passenger sees. In formal terms, the velocity of the ping pong ball is the velocity of the origin of the body coordinate system measured from the inertial frame of reference plus the velocity of the ball measured with respect to the body reference system. This becomes much clearer. But there was one pending task. you cannot tell in a relatable way to the audience the value of this velocity. Why? Because you don't know how to represent the quantities measured in the body reference system on the global reference system. Okay, you notice that it becomes easier to estimate any kinetic parameter if you can split their construction using global and body reference systems. That's why this combination is so powerful in multibody dynamics. In our course, we deal only with planar cases and study the movement of particles rigidly attached to the moving body. The example of the car is far more complicated than the ones that we will be touching in the course. The important message here is that we always need a global reference system to convey the information as engineers, and in many cases, we could make the use of a body reference system to help us to simplify the problem. How to finally transform the body reference system quantities into the global coordinate system? That's a topic for our future lessons. Don't worry, this is a straightforward mathematical procedure that you only need to learn once. Thanks for watching and see you soon.